So welcome everyone to this open day in the ToughSteel project. My name is Erik Olsson. I work as an associate professor up in Luleå University of Technology, and I will share this open day. I spent some time yesterday figuring out where everybody came from and marked it out in this map over Europe, and I see that we are fairly well spread over Europe. Myself and my colleagues up in Luleå, we are sitting up in the northernmost part of Sweden, marked up there with green, and also our friends from Gestamp Hard Tech sit up there. The picture to the right is how it looks outside my office today, and I guess it doesn't look the same for all of you around Europe now. It's pretty exotic up here now. I just discovered also that it's almost 4,000 kilometers between me and the one furthest south in Spain. I think this is very exciting to do. The agenda for today, just a few minutes now, I will wish you all very welcome to this day and present what we're going to do today. After me, David Frometta from EuroCut, he will present the project ToughSteel, present the consortium and the project webpage. And at 1:30, Professor Daniel Casellas will give an introductory presentation of the concept, essential work of fracture. After that, we're aiming for a very short break to get your blood circulation going on again and grab a short coffee. And after that, we will have some shorter presentations. One about an introduction to the fracture toughness database given by Pierre Bollen at UCL. Presentation of the user guideline by Laura Greffé at EuroCut. Will present all upcoming events of the project. It will be done by Michael Tedesco at CRF. And we'll end with an open discussion about the presentations today and what we will do in the future. So I will directly now leave the word to David Frometta. Let's stop sharing my screen now.
Okay, I'll present mine. Thank you, Eric, for the introduction. We'll start with the first presentation of the session today. I hope you can see it. It's okay. Okay, then, well, as Eric said, my name is David Frometta. I'm a researcher on the unit of metallic and ceramic materials of EuroCut. I'm the project coordinator of this ToughSteel project, and in this presentation, well, I'll try to give some words to explain a little bit what is the ToughSteel project, the main objectives, as well as the consortium, some of the main activities planned to be carried out during the project. And finally, talk a little bit about the expected impacts and also different communication channels of the project. Well, first, let's start with some general information about this ToughSteel project. The full project title is Fracture Toughness as a Tool to Address Cracking Problems in Forming and in Service Performance of Advanced High-Strength Steels. The project acronym, of course, is ToughSteel. This is a dissemination project, which means that all the main or the core activities of the project are related to the dissemination and valorisation of this fracture toughness approach in high-strength metal sheets. ToughSteel is a European project, which is funded by the Research Fund for Coal and Steel. It has 2 years, it has a duration of 2 years. It started the 1st of July of 2021, a few months ago, and it will finish by the 13th of June of 2023. The project consortium is formed by 8 partners from 4 different countries and from different European countries, and it is coordinated by EURECAT. Now, if we take a closer look to the consortium, as I said, it is formed by 8 partners from across Europe. Within this consortium, we have 2 universities, Catholic University of Louvain and Lille University of Technology, 1 research institution, that is EURECAT, 1 end user, which is the Fiat Research Center, or CRF, which belongs also to the Stellantis group, 3 steel associations from Spain, Italy, and Sweden. And those are UNESIT in Spain, Associazione Italiana di Metallurgia in Italy, and Yercontoret in Sweden, and also 1 standardization body, which is the Spanish standard organization UNE. Regarding the motivation or the objectives of the ToughSteel, well, the main objective of this ToughSteel project is, as I said, it's a dissemination project. So the main objective is to spread the word, among the steel sector and also the sheet metal forming in general about the benefits of measuring fracture toughness and to understand the crack-related challenges in high-strength metal sheets. For example, problems of edge cracking, or problems related to limited formability or fracture during crash and so on. So there are problems that are frequently reported, and with the development of new high-strength steels are more and more frequent. So the idea is to gather all the knowledge we have gained from more than 15 years of research in the field of fracture of sheet metal, both in internal research and European funding projects, and make it publicly available and also easily accessible to the industry, and to all the stakeholders interested in the benefits of this fracture toughness approach, because we are convinced, and the results have demonstrated that this approach will contribute to improve the efficiency and the competitiveness of sheet metal forming processes involving high strength steel sheets. For example, can help to prevent production losses, maybe caused by the occurrence of unexpected fractures during serial production, for example. Also can help to reduce the time to market of new high performance sheet materials. Regarding the methodologies proposed in the ToughSteel work, there are different testing methods available in fracture mechanics standards and so on in the frame of fracture mechanics to properly measure the fracture toughness of thin metallic sheets. But, well, as you will see, this ToughSteel project is mainly focused on the essential work of fracture methodology, which has been shown to be one of the most suitable methods because of the simplicity and also the suitability to evaluate this crack propagation resistance of high strength metal sheets. So, well, the main problem with this standard of this method is there is no standard method available yet. So, in one of the projects, which is called Form Planet, the recently finished project, we have developed a first step towards the standardization, which is a 10 workshop agreement. Well, also we try to describe the methodology and also give recommendations about sample preparation, etc. The main advantage of this method, as I said, is quite simple if compared to other standard methods of fracture mechanics, standard procedures, and we have successfully applied in different research projects from ToughSheet, ICAT, Optical PAP, or also the recently finished Crash and Tough and for Planet. We have used this methodology not only to optimize the design of new advanced high-strength microstructures with optimum fracture and crash resistance, but also to improve our material selection and also to understand this cracking behavior of high-strength metal sheets during forming on their impact loading. I will not go into many details in the methodology because it will be further explained in the following presentations. But also you will hear a lot about this essential work of fracture, not only in the event, but during all the ToughSteel project. So because this is the main idea of the project, so that the community, the industrial, academic, and scientific community starts getting familiar with this fracture toughness approach, with this essential work of fracture, and how can be applied to understand these cracking challenges in high-strength metal sheets. Well, as the name of the project implies, the project is mainly focused on these advanced high-strength steels. As you know, advanced high-strength steels are these high-performance steels which play a key role in the automotive industry, which are characterized by showing very high strength and relatively good formability. And they play a key role in the development of lighter and safer structures in the automobile. However, the truth is that these older methodologies and approaches proposed in the project also can be transferred to other industrial sectors, also working with these high performance sheet materials or high strength aluminum alloys, etc. Regarding the main activities of the ToughSteel, here are summarized some of these main activities that will be carried out during the project. During this first period of the project, during the first months, we have worked a lot on collecting and organizing all this fracture toughness data from the literature, also from previous RFCS projects, and also from academic works, masters, and PhD thesis. The idea is to organize all this data and to help also to create a fracture toughness database that also will be presented later in the presentation. The idea of this database is also not to put or to collect all this fracture toughness information we have spread about the literature and so on in a single point, so it can be easily accessible to the people interested in these measurements. Because it's true that there's plenty of literature about this fracture toughness or fracture toughness information in the literature and also in thesis works, but it's quite difficult to find a single point where to find all this information together. Also, during these first months, we have been working on the creation of a user guideline. Well, we provide different recommendations about the different testing methodologies, the definition of the different fracture resistance parameters, what are the meaning of the different parameters, of the different standard methods, alternative methods, how to apply these fracture toughness measurements, from at the different stages of the high strength steel development, from the design of the material to understand the role of microstructure on the fracture properties, to the final application for material selection, or even to understand real cracking problems during production. Also, this guideline includes some examples of successful industrial case studies where we show the applicability of this fracture toughness method to understand or to predict cracking problems in serial production. Also, for this project, we have planned a problem-solving open call. So the idea is to organize this open call to enroll 3 to 5 industrial partners, so as industrial case studies, to show also the applicability of these fracture toughness measurements to understand and solve crack-related problems. Also, different academic and industrial events will be organized along the duration of the project. So the idea is to introduce the methodology and also facilitate the discussion with the industry and also with the academic and scientific community. Finally, some standardization activities will be performed also during the project. Some of these standardization activities are the identification of the standard methods and the presentation of the essential work of fracture to relevant standardization committees. And finally, also the publication of this white paper summarizing also the results in those successful case studies and aimed at disseminating this fracture toughness approach or the benefits of the application of these fracture toughness concepts. According to this, well, what we expect from the ToughSteel, we aim that at the end of the project we can provide to the scientific and academic and industrial communities the necessary tools to improve material selection when talking about high strength steels, specifically in advanced high strength steels, so that we can help to improve the material selection in cold sheet metal forming, and also to guide the design of new advanced high strength steel microstructures with improved fracture properties. Also, and new tools to improve part performance prediction, since as we will see in the following presentations, this fracture toughness can provide relevant information about the in-service performance of the high-strength sheet metals. I'm talking about cold forming and the cracking during cold forming, or also the cracking tendency during a crash event. And finally, of course, how to use these tools to reduce the time to market of new material solutions. Finally, some words about our main communication channels as an important part of the communication or of the communication activities. We have created this ToughSteel website. It will serve as a central point of entry for all the public material that we will develop during the project, including basic information, activities, and events, and so on. This website is translated into 6 different languages, including English, French, Spanish, German, Italian, and Swedish. Well, as I said, you will find in this website general information about the project, some news and events, also the information regarding webinars, workshops. Also, we will inform you about the future open call. Also, all the information that we will present during these webinars will be recorded, and also the presentations will be uploaded, so they will be available in our website. Also, it is important to mention that this fracture toughness database that we are elaborating the project will be publicly accessible through this website, as well as the user guideline with the recommendations for fracture toughness testing of high-strength metal sheets. Also, we will have a different section to upload also the scientific publications resulting from the research activities carried out in the project and for public deliverables. Finally, also to comment that we have created this LinkedIn channel, so where we also update all the information, relevant information related to the project. Well, it will be updated with audiovisual and digital promotional materials, also press releases producing on project results, so news related to this sheet metal forming sector and fracture toughness, as well as the participation in conferences and fairs and so on. So if you want to stay updated about the most important news and also related to the project and sheet metal forming and fracture, can join us to this LinkedIn channel. And well, that was all from my side. This was a brief overview of the project. So thank you very much for your kind attention, and I hope you really enjoy the rest of the presentations of the event today.
To the project. If you have any questions now, you can write them in the chat and I can read them out loud to David, or maybe raise a hand. I see nothing in the chat so far. I see no raised hands in the attendance list. We have an open discussion in the end, so it's possible to ask and discuss then as well. I will just show the agenda once more. Let's see where it is. There it is. So now Professor Daniel Casellas will give an introductory presentation of the concept essential work of fracture. So the floor or the internet is yours, Daniel.
Thanks, Eric. Internet is mine. This sounds really super. Let's see how I use it. At least the screen is mine for a while. Okay, so I'll start sharing the presentation. Hopefully it works. Is it working, Eric?
Yes, this looks nice.
Okay, so my name is Daniel Casellas. I am the scientific director at the EURECAT, the Logical Center. I'm also adjunct professor at the Solid Mechanics Division in LTU in Sweden. My background is in fracture mechanics. Since my PhD, almost more than 20 years ago, I work in the evaluation of the application of fracture mechanics to understand performance of materials, failures, and so on. And for a while after the PhD, I started working in formability of high-strength steels, because at the 2000 it was the time where the high-strength steels start to impact the market. In Catalonia, EURECAT, we work close to the automotive industry. We are an automotive country, and we were very close to that problem at that time. And at about 2006, so we start seeing the first cracking issues in forming. And that's where I thought, okay, that's the time to apply again fracture mechanics. But we start working in 2008, the first paper is in 2008. But as happens in research, probably the sector is not ready for a huge change in the way of the way addressing problems. So it took a lot of time to get this into the market. So our first funded project was an RFCS, the ToughSteel project in 2014. And since then, a lot of different projects were funded, collaboration with industries, with the steel sector, with the aluminum sector as well, car makers, part makers. And now this is the end of this trajectory. It started almost 10 years ago, the ToughSteel, because as David told before, this is a dissemination project. So this is when we want to share with the engineering community, scientific community all around Europe, how we think fracture mechanics can help materials design, can help part production, and can help at the end understand formability problems. So in this session, in this lecture, I will try to show how we can use fracture toughness to understand what we call crack-related problems in sheet metal forming. First, on how everything begins. Well, this is again about the evolution of high-strength steels in the automotive market. This is a video you can find on YouTube about a crash comparison between a vehicle more or less designed with current steels, high-strength steels, and 20 years ago. I guess that you know what's going to happen. So our cars right now, current cars, are safer and lighter than before. I think that these images are explaining what I mean. I prefer to be in our cars right now, in the current cars, than in 20 years ago. So clearly, high-strength steels did a really good impact into the sector. They really increase crash worthiness. They also reduce weight, or at least allows to contain the weight increase in designing modern vehicles, mainly thanks to the highest strength values. But these high strength values are also associated with a limited cracking resistance, and this is what happens, or this is what may happen. This is a picture of a lower side of a B-pillar. It is not nice to have a crack here. Of course, this is not something that we want to have in a component that has supposed to direct low path during crash. So here a crack will absolutely destroy the initial design of the component. So it will not perform as expected. So because we are material scientists, we are happy that new materials bring new challenges. This could be the last slide of my presentation, because this is the end. This is what they're going to show in the last picture, that what we call crack-related problems, like edge cracking or like crash worthiness and so on, can be explained by the measure in the fracture toughness. So that's the end of the presentation if you want. So you can come back after the coffee and you can look at the presentations. But we have 30 minutes ahead. I would like to share with you how we reach to these conclusions. and also, or mainly by addressing the questions that pop up recently for this. So the first is, okay, this guy showed me in the screen a cracked component. So should I really be concerned about its cracking? Should I be concerned about cracking issues in sheet metal forming? I think yes, you should. And okay, well, fracture toughness. I know that fracture toughness has been an old property measure since the 60s. It's been widely used in pipeline constructions, in pressure vessels, in containers, in the ship and naval industry. Should be easy. Well, the answer is not. The answer is that we have how we measure fracture toughness in thin sheets. And at the end, after these long difficulties in testing, and after these years you told me you have been working with, okay, how can I benefit from fracture toughness? What can fracture toughness do for me? So this is going to be the outline of the presentation is here in the screen, and this presentation will run trying to answer these 3 questions. So I start with an introduction to the problem, like with construction in vehicles and the formability in high-strength steels, and introducing or remembering this concept about global ductility versus local ductility. Then I will continue with the fracture mechanics approach, how we think from a fracture mechanics perspective that the toughness can be measured. Of course, introduce the essential work of fracture and compare with other elastoplastic fracture mechanic tests. And at the end, show what we can benefit from fracture toughness, what we can get at the end, and you will see that this especially evaluation of the material properties for new steel development, understand its cracking and crash resistance, and also assess the quality of the raw material. So let's just start with the first section. Why should I be concerned as an engineer or as a researcher about its cracking? Well, you should be concerned because automotive, this is a very old picture, but it illustrates how important is sheet metal forming in vehicles today. If you look at the mass breakdown for a vehicle, it more or less changed recently, but the distribution is similar. Bottom white and chassis parts account for almost half of the weight of the vehicle, and these are made by metal sheets. So everything that is important to that, everything that is related to lightweighting for those parts is relevant for engineering. Of course, the problems in bottom white and chassis are different. And more interesting now, we have a development of the powertrain. So powertrain, batteries, also the battery cage, everything around batteries to protect it from impact and so on will be also made by metal sheets. So the proportion of metal sheets in a vehicle will increase in the coming years. That's clear. If you look at the well-known materials that can be used in vehicles construction, if you look at the density, steel is the denser material, titanium, aluminum, magnesium, composites. But at the other times, if you look at the prices, this is clear what is competitive. Here I didn't put the sustainability. We know that is a main factor today for materials development, and clearly steel is the winning in this competition. Is absolutely recyclable and has no dependency on critical raw materials. So all the news that we are hearing today about the dependency on the critical raw materials from other out of Europe, steel is not affected by that. So I think we are in front of a great material. We know for more than 200 years, but I think that we should still we will continue knowing from this material in the coming years. Just a picture of how vehicle sector is addressing lightweight. This is not a single solution for a vehicle. You know that it depends on the size of the vehicle. It depends on the utility for that vehicle. It depends on the production scale. Like this is clear that because of the cost, because of the product production rates, steel is again the winning material in large scale production, and is supposed to decrease in favor of aluminum and composites in luxury, electrical, or medium scale. But again, this is a picture from maybe 5 years ago, and we see in the automotive sector that this trend is not like this. Steel is still the material choice in many new designs. And because we are in a dissemination project of steel, I would like to share with you good news for the steel makers, good news for metallurgists. Maybe you know that, but just to highlight, this is the picture of the BMW, a small electrical vehicle. It was the first production vehicle produced by serial production vehicle produced by carbon fiber reinforced polymers. But 2016, this is a news from Reuters. This is not something that is just picked from the web. This is a news that the German group, because of the cost, the recyclability, the problems in manufacturing, and so on, decides to go back to aluminum and steel for most of its electrical vehicles. So good and interesting challenges for CML for me. And also for Audi. Now here talking about Audi has been a brand that is specialized in aluminum, but 4 years ago, this is also a news from Audi website that Audi, at least the A8, but also the Q4 and some other electrical vehicles are back to steel. This is the bottom white picture given by Audi itself, and you can see that the steel, this is purple and this light green, steel sheets are back to the bottom white. Here is about 40% of the steel. So yes, we should be concerned about everything that is related to its cracking because the steel is here. Advanced high-strength steels, I don't want to explain so much about this because you probably know. The advanced high-strength steels are usually shown in the banana plot. People typically call it this plot banana because this is a representation of the elongation, ductility, in terms of tensile strength, and the higher it is, the better performance because you're supposed to combine formability and strength. We can consider that our high-strength steel is about this limit, 600 to 800 megapascals. So we have different microstructures, we know all of them, and it's an area of current research working here. The third generation of high-strength steels is coming. At the end of the presentation, I will show you how we see the banana plot in the coming years. Maybe it's not banana anymore. We have to find for a new name. Yeah, advanced high-strength steels are widely applied in the bottom white. Here you have the different strength grades in different parts of the body, about 60% or even more for some vehicles. Is this, and if you look at the evolution, when it starts 20 years ago in 2000, mostly low carbon steels and steels with, in that time they were called high-strength steels, but no more than 800 megapascals. If you look at the situation today, this is a breakdown for 5 years, but it doesn't change so much. We see the introduction, the big introduction of press-hardened steels, and a big proportion of really high-strength steels, more than 800 or up to 1,000 or 1,200 megapascals of strength. So, just some figures to show you that this evolution. This is the picture is provided by Volvo, the new XC90. Some years ago, and one of the last developments, the amount of press hardened, this is press hardened, increases clearly in the vehicle. Or if we look to more, not modern, but at least fancy cars as Tesla, we see again a higher proportion of high-strength steels and ultra high-strength steels. That means press hardened steels. Just some insight about the microstructure, because high-strength steels has many different microstructure that, of course, gives at the end the properties for them. We have what is called dual phase. It's a combination of soft phase ferrite, hard phase martensite. Nice ductility because the ductility, the formability is given by the ferrite, and high strength because of the martensite islands. If we increase the amount of high resistant phases, I mean martensite or benite, we can have the trip steels with some retained austenite. Remember that trip steels has the ability of produce plasticity during the deformation, induce plasticity during the deformation, because of the transformation of retained austenite to martensite that hardens the material during deformation. This is expected to have high formability associated with high strength. The complex phase steels, as the name say, is a complex with microstructure combining almost everything you can find in the steel, bainite, martensite, retained austenite, ferrite sometimes, carbides. And at the end of this progression of different phase assemblage between soft and hard phase assemblage, we have martensite with a higher strength and of course lower ductility. We will discuss these microstructures in terms of fracture toughness in the coming slides, so please keep this in mind, or at least if you check again the presentation, you can come back to this to compare what I'm going to tell you in the coming slides. Yes, this is the way or the path from mild steels to high strength steels. Definitely high strength steels, GL strength is higher, tensile strength and crashworthiness. We know that experimentally. This allows decreasing the sheet gauge, so the thickness is lower, then it's a lighter material, but formability is compromised. We know that because we have edge cracking problems in forming. We don't want that. This is one of the problems that hampers the definitely application of high strength steels, of high grades of high strength steels in many applications. The forming problems, you cannot afford for 1 or 2 cracked parts in your serial production. This is absolutely not efficient. So I like this as a researcher. New challenges we have to face because these new materials are very interesting. Let's just make a step back and remember how we classically address sheet formability. Sheet formability, when we talk about deep drawing or conventional formability, we think about tensile stress, tensile tests. The higher ductility is supposed to have higher formability. Increasing the N values, the slope of this range of the curve is also interesting because it allows to homogeneously spread the thickness and then increases formability, reduces neck localization. This is tensile test information. And traditionally, the sheet forming sector is using also what is called the forming limit diagrams. Because in metallic sheets, the deformation is difficult to measure through the thickness, so it usually measured in the surface. So using DIC techniques, it's possible to follow the strain distribution during forming. Following this strain distribution from a dot, from the major and the minor strain, we can plot a curve where we can see the areas that are failing or necking or fracture is happening, and we can also see the areas where the forming is safe. So this is what we call the FLC curves. Some examples how it works. This is taken from the literature. We see a part that has been formed with a crack here. If you look into the modeling, this is the FLC and the FLD diagram. These points corresponding to the crack are above the curve, so are in the fail or unsafe area. Then it's a crack, so definitely works. Another example of like a B-pillar shape. Some fractures here in this part. This is clearly because of thickness reduction and necking, and this modeling can capture this. Experimental FLDs are above or below the modeling points for the fracture. So good prediction. But in some operations, this approach fails. We know that this is an example of a part that all the modeling, all the simulation points in this area are below the FLD, so it's supposed to be in safe conditions, but we definitely see a crack. So this is what is called edge cracking. The cracks appearing from the edge and growing through the material that cannot be predicted for conventional sheet forming approaches. So let's explore in this concept about edge cracking. So let's just make an exercise, see how we can understand this. This is a fake part, just to show what we want to do. If we use a normal low strength material or high, this is a low alloy steel with a yield strength of above 400. If we want to reduce the weight, we have high strength steels. For instance, we can choose a material of a 1000 megapascals strength, a CP or a TP, complex phase or dual phase. We get a 50% weight saving. That's super. We go for that. Let's do it. So how we conventionally did it many years ago. Okay, we look at the tensile curves. Yes, say yes, select the one with higher formability, higher ductility. This is DP1000. I choose this. But just to be sure Okay, let's do an FLD diagram with this material and look at the modeling. Clearly points are below the FLD. Let's go for that. But this is not working, because to build this component, we start from a metal, from a steel coil. We cut it in parts, and for that, we separate it, we trim the edge. We also make a hole in the center, punch. So these are affected parts. After that, we form it, we bend it. And what was happening here? That these areas to stretch flanging and hole flanging. And the result for that is this cracking here in the expanded hole, or cracks in the edge in the flange area. And all of these are, remember, below the FLDs. So this is definitely a problem. How to deal with this? Yeah, it's because in these operations, in the forming operations, we see the edge, we see the damage on the edge. Let's see how edge damage is affecting the formability. This is a part that has been laser cut. So in principle, the edges are not so much affected. So when these parts are formed, we see the cracks here, but these cracks are because of a strain localization. And these cracks, if we look at the FLD and the modeling, can be explained. This is where the part fails, and these points here are above our FLD. We look into the fracture. This is a strain localization. Okay, this is conventional formability, so FLD works. But what happens if we cut it? What happens? This is the same part, but with a mechanical cut, and the situation is totally different. We have the crack origins associated to the surface conditions. It really starts at the surface. We see micro cracks, and we couldn't see almost strain localization, almost no necking. So the fracture is fast, localizing without necking. This is the characteristics of edge cracking. We should look at the edge damage then. If you compare a damaged edge and the non-damaged edge, we see the difference in the edge cracking appearance. So where this edge damage is coming from? It comes from the forming process. This is a profile of a cut edge. This is the blank. This is where the punch come in and the punch come out. We have a rollover area first, a shear area, and a fracture in the burn. If we look step by step, this is a punching or trimming process. This is a point where the cracks appear here and grows through the surface. This is an image from these areas here. After some displacement of the punch, the deformation is high enough and the cracks appears and grow. So at the end, in these surfaces, we have cracks, we have irregularities, we have voids, residual stresses, so everything that can be related to damage. This damage is happening always, or is difficult to control. Yes, this damage is in a large production or in a serial production process. Damage comes from many places. Cutting clearance should be well adjusted. Cutting clearance change with cutting tool wear. If we change the wear conditions, you see how the fracture of the sheet looks like with a new punch, with a worn punch, because the effective clearance changes. Clearance clearly affects the fracture surfaces of a sheet. This is the top view from this side. 8%, 10%, 12%. We see the difference in the fracture and in the varnish areas. Also, cutting speed, machine stiffness, coaxiality. So damage can be easily introduced in materials. At this point is where the concept of global formability and local formability is clear. We can differentiate when we talk about sheet formability. In global formability, as understood as the ability of a material to undergo plastic deformation without formation of localized net, and the strains can be uniformly distributed. This happens in conventional drawing or in plane strain, where the large regions of the material deform If we talk about global ductility, remember the classical approach works, forming FLC, elongation, strain hardening from tensile test, that's perfectly working. But when it comes to local formability, edge cracking problems, this is another problem. We can name as a local formability the ability of the material to undergo plastic deformation in an area without fracture. This local forming includes strange flanging, hole expansion, tight radius bending, and so on. And the way we can measure it, well, there are some experimental, quite experimental tests based on strain and fracture observations, like the hole expansion test, the true fracture strain reduction area of fracture in tensile specimens, also the bending angle. These properties are quite easy to get, or these parameters, but are not really mechanical properties of the material. So as a material scientist, we would like to know which is the material property that we can use to understand cracking. The answer to that is the fracture toughness. So fracture toughness, measuring the frame of fracture mechanics. This is important, not Sharpie, not strange ways of measuring toughness in the frame of fracture mechanics using a crack. And this is how we measure toughness, and this is how we see the solution for these edge cracking problems. So the next section. Okay, fracture is relevant. How we can measure it? I will explain you how is the approach from fracture mechanics, what is the essential work of fracture method, and how other elastoplastic fracture mechanic tests can be compared and used. Well, if we think about fracture mechanics talk about cracks or deal with cracks. And we see in the previous slide that cracks are there when it's about forming of trimmed or punched edges. This is the SEM picture from a cutting from a shear edge. We see micro cracks. At the end of micro cracks growth, and in the part we see the real here the large cracks or visible cracks. So we start from an initial damage, an initial crack. This crack grows and becomes an edge crack. So if the crack propagation is the parameter that governs the initiation of the crack to the final edge cracking, fracture toughness is our property. Toughness is the property we have to measure. So let's talk about fracture mechanics. In the here we have what we conventionally, or what is conventionally thought as the toughness from a tensile stress strain curve. Remember, the area under the curve doesn't work for that. The area under the curve of a tensile test is the energy spent in a tensile test, but does not account for fracture toughness. So this cannot be used. We cannot use linear elastic fracture mechanics because the steels are ductile, so the plastic zone is high. We cannot use the easy plane strain fracture mechanics. We have to come to elastoplastic fracture mechanics. And here we have old methods, old or well-established methods like the J integral, the JR curves, the CTOD. These are well described in standards, but are experimentally complex. So it's nice. It's a nice lab work. It's a nice research work, but definitely implementing this into industry is not really straightforward. So how to measure fracture toughness in thin sheets, in thin ductile sheets? The answer, you know the answer already, is the essential work of fracture methodology. This is not new. I would like to say that we invented, but we didn't. This is a method that was developed in the 70s. It was initially developed for understanding the tearing resistance of ductile sheets. It's a nice work. There is I would say quite many papers from the 70s to the 90s with this. But the problem for high strength steels wasn't at that time, appears in 2000. Because of its simplicity, it's successfully applied in polymers. In fact, there is a protocol from the ASIS to measure this, and also something applied in ductile metals like low carbon steels, copper, and aluminum alloys. But again, when the massive research was conducted in the 90s, the steels applied in automotive, the steels that use the sector, didn't need that parameter. They were ductile enough. So the problem came afterwards. And well, as I told you in the beginning, we started in 2008, but our first funded project was the ToughSheet, together with Center of Research of Fiat, together with ToughSteel Open, together with IDIADA. We developed this project called ToughSheet, where we apply this methodology to different high-strength grades, very different families of high-strength steels, and it really works. So this is the journey started almost 10 years ago, and now here explain you the application. So first, let's explain you how it works. This is not magic. This is fracture mechanics. If you look for a crack, this is a draw of a crack. If we are in a brittle materials, we don't have plasticity. When the stress intensity factor at the crack tip reaches the fracture toughness, it grows, and that's it. And we don't have to worry about plasticity, or not so much. So easily to evaluate fracture toughness in brittle or quasi-brittle materials. But in ductile materials, in front of the crack, we have a fracture process zone where all the cracking situation takes place, and it's surrounded by a big plastic zone that is also depends on geometry. So if we want to understand what happens here, just in front of the crack tip, we have to be able to separate the plastic work and the fracture work. So we can say that the total work of fracture can be divided in the plastic and in the fracture work. We call it essential work because this is related to damage. This is surface creation and necking. This is essential. This is what the material itself, the microstructure, does. This is why we call it toughness. And the surrounding plastic work, this is plastic deformation. It depends on the spacing geometry and size and the loading mode, and it's not essential. It depends from specimen to specimen. So the point is that we have, when in a fracture test, we have to be able to separate both terms. This is not easy, unless you use the essential work of fracture methodology. How it works? Well, so let's look at this specimen. It is a double edge notch specimen in tension called DNT. 2 notches on the edge, tensile loading. If the area or the volume between the 2 notches is completely tilted, and the plastic zone is confined here, I mean, we don't have plastic zones around the specimen, we can effectively separate the total fracture work in the energy for fracture plus the energy for plastic deformation. Because this is related to area, this is fracture, this value is proportional to area. Here is the area. We can just define a new parameter that is material dependent, not area dependent. And this is the area. This is the ligament length and the thickness. So this is the cross section of the specimen subjected to tension. And the same for the plastic work, but now because plastic work is proportional to volume, we have to include here the volume of the specimen corrected by a factor. Okay, now we see that if we divide the total work of fracture obtaining in the tensile test of these DNT specimens, if we divide it by the area, we get this. This is independent of the ligament length, and this is dependent on the ligament length, the separation between the both. Then this is a nice mathematical artifact, because if we test specimens that are geometrically similar, but only change the length of the ligament between the 2 crack fronts, we obtain these self-similar low displacement curves. And because this is a linear expression, if we plot this value, okay, the total work of fracture here divided by the area, LT, we can build this nice linear plot that, according to this, if this line is extrapolated to the y-axis, this intersection is the essential work of fracture, is the energy for surface creation, is the energy you want to measure. So if we do that, if we plot the energy divided by the area for different specimens having different ligament length, and we get a linear trend, the interception of this ligament, of this linear trend to the y-axis, give us the fracture toughness. Of course, if we don't have a linear relation, we have to think what happens here, because this model will not work. But if we follow this, then this is. What is interesting from this method as well is that if we detect by DIC methods or by optical methods, we detect the initiation of the propagation, we can also get the energy at the beginning of the crack initiation. And because this is just when the crack starts to grow, this is independent from the ligament. So the method is simple, no need for crack monitoring, only load versus displacement curve. We can separate initiation and propagation. Now we see how we use that for understanding things. Keep in mind, initiation is the energy for the crack starts to grow, and total work of fracture is the total energy that the material uses for fracturing. And the method can be used to different specimen geometry. In the coming presentations, Laura will explain how we can use another specimen geometry. But this is some results from different materials: complex phase, third generation steels, conventional partition, press hardened or trip high manganese steels. This is the values of initiation, the values of the final fracture. You can see that depending on the steel, this is a difference between the initiation and the propagation. For instance, dual phase steels has a close distance between the initiation and the propagation. And this is seen in this video. This crack grows very fast. When it starts, it grows very fast. On the contrary, if you look at that video, when the crack starts to grow, it takes a while to fracture, because the energy during propagation is higher and higher and higher. So this results, this separation of initiation and propagation is consistent with what we see in practice. A material that can withstand crack propagation and a material that has a low crack resistance. Of course, there are some other methods we discussed, like the J-integral or the Can-type TR test. These both are standardized, but in the case of the J-integral, I don't know if you have worked with this. The methodology is complex, requires crack monitoring. It's not a friendly technique to use, but gives results. The problem for these specimens, and also this, is the loading mode, because after the crack starts to grow, the specimen starts to buckle on the crack tip, starts to have bending and compression here. So after a given point, the results we get with these specimens are not really related to the fracture propagation, because it includes also compression and plasticity associated with the specimen geometry. So initiation, I think it's something we can rely on. You will see in the coming slides. But the extent of the energy use, it increases, because the more we open the crack tip, the more compression and bending we have on the other part of the crack. So this total energy is not really clear. The standard suggests to use this, and this value can work sometimes, but sometimes not. We will see this. Regarding Can-TR test is similar. We can also estimate the initiation of this, but again, the values we get from these parameters, from the energy initiation and propagation, overestimate fracture toughness, mostly because of the crack is not growing in a similar tension mode. So this is the picture that compares initiation and propagation energy. You see that initiation resistance, when the crack starts to grow, for compact tension, DNT, essential work of fracture, J-integral, or the Can-TR test, it's almost similar, because the crack is just at the beginning. It hardly see what is ahead of it. So with this, initiation is more or less independent of specimen geometry. In the Can-TR test, we see this is the results from Can-TR test that clearly overestimates the toughness compared to essential work of fracture, because again, this is a lot of energy contribution from plasticity. If you look at the comparison between the JC and the essential work of fracture, for some materials, some high-strength steels, it works pretty okay. But from some others, this is a noticeable difference. It happens in these materials, complex phase, or similar materials that has a large energy contribution from propagation. So if we cannot properly capture the energy used in propagation, we are not properly estimating the toughness. So for the materials we are really interested, the ones that have higher energy absorption, J integral underestimates. Is really a conservative way of measuring properties. So we see for the comparison that sensible diffraction is the better way to quantify crack propagation in high strength steels. And now we will see in the coming slides that this parameter is perfectly explaining what happened in these two conditions. So now let's see what can fracture toughness do for me. How can I use that? So first, let's think about microstructure. If you remember the slides about microstructure, we have microstructures that are clearly dual phase, like with a ferrite soft phase and hard phase. These are what we call DP-like microstructures. In these microstructures, the voids are accumulated in the soft area, so that the void generating the cohesion of the ferrite martensite interfaces. And if we look at this DP-like, like this, the toughness is low because once the cracks appear, this is no energy for the system to release, and the cracks grow mostly following the martensite islands that are brittle. On the contrary, on CP-like microstructures like this, we see that the toughness is high. Toughness is high because it's homogeneous, can dissipate energy during a propagation and so on. If you look at other microstructures that are not higher toughness but are homogeneous, like martensitic microstructures, we see that toughness is more or less similar. It's not a big variation, because again, the more the homogeneous the microstructure is, the higher or the more homogeneous the toughness is. So fracture toughness can be used also to understand the effect of microstructure on the properties. Another example is if we want to assess the contribution of the trip effect, the information-induced plasticity in fracture toughness. This is you can find more information in the papers you see in the slides. In this case, we compare two materials, named A and B. One has a trip effect, so both are third generation of high strength steels. If you look at the formability, at the conventional global formability, the trip effect contributes to better ductility. But if you look at the sense of work of fracture, remember, work of fracture ligament length interception is the fracture toughness. The one having trip effect has lower toughness. So the trip effect improves global formability, as is well known, but is not improving the fracture toughness as well. On the contrary, it reduces. If we look more in detail in the microstructure at how the cracks grow in these materials, we see that in the retained austenite that is transformed to martensite during the crack propagation, during the deformation, this martensite contains higher carbon than the fresh original martensite, because retained austenite has been enriched by carbon during the quenching and partition process. And this high carbon martensite is more brittle than a low carbon martensite. So when in a trip effect steel, the retained austenite transforms to martensite, it produces a more brittle net of martensite that guides the crack to grow, that eases the crack to grow. So in trip effect, the propagation of the crack is along this hard phase that is harder in trip materials, than in not trip, because of this brittle martensite. This is a picture of the crack. This is this picture, and this is the measure of hardness by the indentation, and you can really see that the crack is growing to the high hardness martensite. Well, let's now focus on edge cracking. This is the plot for many different steels with a hull expansion ratio is a well parameter to define strength frangibility in the industries. We see a nice trend for many different microstructures, third generation, conventional dual phase, many different steels. This is a nice correlation. So the higher the toughness, the higher hull expansion ratio. So it's supposed to be also useful for its cracking. So if you remember the fake specimen I showed you in the first slides, now come back to this. And this is again the competition between dual phase and complex phase. If we choose a dual phase for this material, we will have cracks. If we choose complex phase materials, higher toughness, complex phase, we will have no cracks. So definitely, the essential work of fracture, the fracture toughness is useful to predict if a material will or not withstand its cracking. This is the same as the last slide. This is an example of underseat beams in a vehicle. The first material was a dual phase with its crack here clearly seen. If you look at the curve I showed you before, hollow expansion ratio, essential work of fracture, this is the point, low toughness. But if we use a complex phase material with a higher toughness, no cracks. And this is consistent with different materials we try. High strength steels, aluminum alloys, stainless steels, soft materials. So in any material we tried in the last 5 years, this trend is following. The higher the toughness, the higher the edge cracking resistance. Now remember that I said that the fracture toughness is interesting to evaluate from an essential work of fracture because we can split the initiation and the propagation in two. How we can use that to understand things. So this is the specimen I showed you also in the first slides that has been trimmed and bent. And this is the materials that we tried at that time. It was the ToughSteel project. And we see that the crack starts depending on the initiation. I mean, this is the stroke where for the first crack starts. And you see that because the crack starts to appear, it's controlled by the initiation energy. And it's more or less related to initiation energy. But then these cracks will grow, because if you keep on following with the stroke and you keep on the forming, these cracks will further grow. And these are explained by the total work of fracture. So here is for the same materials, the length of the crack at the first stroke that we see a crack appearance, and this is how the crack is, how the crack grew in the forming tests. You see that the cracks that grew more were the ones having less fracture toughness, lower fracture toughness. And the clear case is this: in the complex phase steel, remember in the last slide, high toughness, the crack almost has no change. So when it appears, even you keep on deforming, even you keep putting energy in the system, the material can deform, can withstand the growing, and produces this effect. So I think this is important concepts. Initiation is for initiation, and total energy explains what happens when the crack is fully developed. Let's use this concept also for another problem, that is crashworthiness. We know that crashworthiness is a complex property to measure. Impact tests are time-consuming, expensive, and crashworthiness, as we know, cannot be estimated from tensile test. This is just a comparison of a crash index with different tensile parameters, no relation. So doesn't work. The work is essential work of fracture. It works. Let me explain you why. This is how usually automotive is indexing the crash resistance by the number of cracks. This is the beam or the specimen that is before crashing, and this is after crashing. You see the faults here, and counting the cracks that appears at the falls, at the side, or at the different parts, counting these cracks. If material has no cracks, high crash index. If the material is destroyed, low crash index. And in the middle, depending on the crack length and position, this crash index is different. Okay, if we put this crash index for different materials, we see that the higher the toughness is increasing the crash resistance. Because what we want here is that the crash index decreases in a slow way. Because if it is in a slow way, increases the crash resistance. So decreasing the slope, increasing the fracture toughness. Maybe better in another way of measuring energy absorption, that is measuring the energy absorption during crash. In these coupons that we actually crash, we measure the energy and plot against the fracture toughness. Here works perfectly. We see here two examples. This is it's supposed to be a video, it's supposed to move. but this time it doesn't move. Okay. Here it shows brittle behavior, or no, sorry, not brittle, not so high energy absorption behavior associated with low fracture. And on the contrary, complex phase still shows a nice backlink, nice floating behavior that gives a high energy and also associated with a high fracture toughness. Based on these results, we can make a map to rationalize crash worthiness. This is almost arbitrary, but our expertise is putting this number here, or this limit in this point, that after this value, the materials are safe or has high crash resistance, and lower this value we have not so good. We can also use the initiation energy to rationalize critical intrusion. What is critical intrusion? In this plot of the crash index versus intrusion depth, the intrusion is the point where the damage starts here. So when the crack starts. And if we look at the different specimens, please, the ones with this point cannot be explained because the crack starts for the spot welds. So the behavior is not because of the material, it's because of the spot weld. But in the ones that the crack starts from the material, we see that the energy at critical intrusion is very similar, is consistent with the essential work of fracture at the initiation of the crack. For complex phase, for TDF, for this mixed microstructure, for trip steels, this relation between the initiation and the energy is consistent. So again, understanding what is happening, you can have tools to measure it by fracture mechanics. The same for bending. We did it. The last slides were about axial crash. This is bending. You see here a beam that has been impacted by this catapult, these conditions, and we have a crash part. Here the crash index is calculated following this. This is in the presentation you will have. You can explore this in detail. But at the end, what is relevant is the crash index. Here again, in this value of 250, we see the border between materials that are having no cracks after bending impact and the materials having cracks at bending impact. So safe regime, safe area, higher toughness, cracking materials, not enough toughness for bending. We see, or I show you how toughness can be used to explain edge cracking, how we use to explain crash worthiness. Let's see what happens in raw material, because this is an industrial problem for some of you. We know that the raw material we use in the sheet metal forming, the material we use in the workshop is in form of big coils that are produced in a massive industry. So of course, the quality of the steel is controlled, it's effectively controlled by the steel makers, but some small difference may occur. And when this small difference happens, the coils or the property of the material may change from coil to coil, or within the same coil may change from the tail to the center of the coil. And generally, these differences in the fracture cannot be explained by tensile test. We know that if you change the material supplier with the same steel grade, with the same ductility, with the same yield stress, sometimes the behavior is not so good. But this is not because of the ductility. This is not because of the yield stress. It's because the toughness is different. And if we don't measure it, we don't know it. So let's see how it affects this, which is one example from a steelmaker in Europe that give us specimens from different coils. And just by checking and putting all together, we did detect a big scatter. This is not usual in fracture toughness measurements. The scatter is not that high. But looking at the specimens that were not or were showing strange behavior, looking with the SEM, we detected that the inclusion content and the inclusion and the morphology were different. This is because the metallurgical quality is very sensitive to the toughness, or on the contrary, toughness is really related to the material cleanliness and the material microstructure. So small changes can really be captured, because fracture toughness measured by the essential work of fracture is a very local measurement. So small changes, small local changes can give big result. So we were able to discern this problem in the production of the steel. This is another 2 examples coming from bar makers. This is using the same nominal chemical composition. The certificates, quality papers are the same for both the different steel makers. It happens. We have coils for different steel makers time to time. But some parts show its cracking problem. So they know OK show also larger elongation that the OK specimens. No idea what was happening. We measure fracture toughness, and we clearly see that both in longitudinal and transverse direction, the non-OK material always show lower toughness. So again, a way to assess the quality of the steel. Another example. This is the same steel maker, but different heats. We get materials that are OK and no OK. Again, the same tensile properties, but the toughness in the OK were always higher than in no OK. So this is nice. So how we can see it, how we can measure it in the lab. Laura Griffin after the coffee break will explain you how to effectively measuring this. This is a simple method to obtain it. We evolved from a complex lab test for cervical fracture to a very simple lab test. I think that you will like this approach because it's absolutely applicable. It's straightforward, applicable to material quality assessment in a production line. Summary. The end. My summary is absolutely short because I talk a lot about properties, about fracture mechanics. I will not to put again the same. I will only say that after 10 years of working in fracture mechanics in high strength steels, after 10 years of contributing the metal sheet industry to improve their products, we can say that the essential work of fracture is the best fracture toughness parameter to describe face cracking and crash worthiness. Again, just the plots that many different grades, many different steels put in the same line or in the same trend, also for crash. The last slide I would like to share with you is the banana plot. Remember the banana plot for mobility, elongation to strength. This is the materials we use in banana plot. We see that the elongation ductility doesn't account for fracture in metal forming. So we propose another plot. Is the plotting here the essential work of fracture and here the strength. It's not a banana, it's not nice, we have to find a name for that. But I think this is an efficient way of understanding and selecting materials for sheet metal forming. That was my last technical slide. The last slide is to thank you for your attention and of course, welcome for your questions.
Yeah, for this really nice presentation. I hear my echo. I think we should take a break, but first I saw that it's already now appearing questions to you in the chat, so I can read them for you. It's Henrik Schurin at Scania. You showed low fracture toughness for trip steels. Based on this, what is the future for the 3rd generation AHSS?
Thank you, Henrik, for this question. For maybe I don't want to be in trouble with our steelmaker colleagues, but the thing is that when we start assessing the fracture toughness of trip steels, we really thought that the trip effect was beneficial for the toughness. That was a RFCS project we ran together with Arcelor and ToughSteel Open. They are the co-authors of this publication here. The co-authors of this publication. What we saw is that the trip effect is detrimental for fracture toughness because the martensite is hard. So in this sense, I think that we have to look for another ways of having retained austenite. I mean, maybe less carbon in the retained austenite, that the martensite at the end is not that brittle, and also trying maybe to have more effective distribution of this, not trying to not get the martensitic islands connected. If they are not connected, it will be more difficult for the crack to start to grow. So it's definitely a microstructural design based on the distribution and shape of martensite and austenite is definitely there. So is still developing in that area. That's, again, as I said before, this is it's nice to see the materials are evolving. Thanks for that, Henrik.
I have a question as well from Sean Lamontanara. How edge toughness or crack sensitivity will be put in the material standard, in material certificate, for examples?
Well, this is another fight, because you have to. If we start about the method at lab, we saw that the method works, that is reliable, robust, that can be applied to many materials. We also saw some limitations, and we tried to work on that. But once we saw that it's a robust method, we work in this. This is a CEN workshop agreement that is the preface for a standardization for metal sheets. Definitely, this is a long way, and in the ToughSteel project, there are some standardization activities to progress in this. The thing that the way to that is going together, the steel makers, the part makers, and the car makers, to agree which kind of properties do we seriously need for developing crash-resistant parts. And I know that it's not an easy journey, but we started some years ago. I mean, in the connecting all the value chain in the sector to benefit from that, because at the end, it gives benefit for everyone. It reduces time to market development for steels. It increases the reliability of part designs. It reduces the material losses during production. So I think everyone is benefit. And also researchers from our side, we have a new field to apply fracture mechanics. So definitely the journey is not easy, but we started with this.
And then I have two additional questions from Henrik. The EVF can be used to compare different materials, but how should it, like the form limit diagram, be applied in practice to evaluate the formability of a component? Is there something like a ductile to brittle threshold for the EWF?
Yeah, I don't know if I get the question right, Eric. No, if it's
maybe we can activate Henrik's mic.
Yeah, if Henrik is here, please. Henrik, if you are visible, we can talk about this.
So now his mic is.
Henrik, are you here?
Yes, sorry. Yes, I'm here.
Yes,
hello.
Please.
Thank you for a very interesting presentation. Well, I was just thinking about, I think maybe this question was a little bit related to the previous question, actually. I mean, so I think you have already answered it in the previous question.
Yeah, you talk about formability itself, maybe how to combine both, right? How to combine.
Yeah, no, I was just thinking, I mean, this method can, of course, as you shown, be used to compare different materials. But I was thinking more if there was, and if I have a specific component and a specific material, and how to use it more qualitative and not comparative.
Yeah. Okay. Yeah. There are some thresholds we saw by expertise. It's about 250.
Yeah.
Of course, we should be further. What we can do, what we are working now with quite success, but we don't have time today, isn't the modeling, implementing this in modeling. So that when you form, and the way is to allocate at the edge that are shear, the shear edges allocate the different material properties, a damage behavior, a damage law, specifically for the cut edge. And then we can more or less predict when the crack appears in forming. This would be the way to design with this property. Not only compare, you are right, but once you know that you have these results, this 250, I think that you are pretty safe. But at the end, you have to model it, to simulate it, to see it.
Okay, yeah, but that's some kind of rule of thumb then, to have a feeling what is.
Exactly.
Okay, yeah, that's it. Thank you very much.
Thank you, Henrik.
And then I had one more question.
Okay, please.
That was about the material thicknesses that is suitable for this method. You are talking about thin sheets.
Yes, I know you are a thick.
What is a thin sheet, and how long is a rope, etc.?
Yeah, this is the question for Laura for the next presentation. But you are right. We mostly apply to body white parts because it was the huge market for crash. Less than 3 millimeters was perfectly nice. For thicker, these TNT specimens are quite difficult to propagate the cracks and quite difficult also to load in tension because the loads are high. And then we suggest single edge notch beam for thicker than 3. And it works very well. Henrik, if you have the chance to be in Barcelona in the CHS2 conference at the end of May, 1st of June, we will show some of the results for thick sheets, how to evaluate toughness in thick sheets. So welcome to Barcelona.
Yeah, thank you very much. I will see you there.
Great.
Bye. Thank you.
Bye.
I have 2 questions more in the chat, and then I think we'll leave the remaining questions to the open discussion. We're a little bit over time, but I think that this discussion is so nice, it's absolutely worth it. And the first is from Flavia Gilly. Is the EVF a property that can be kept under control by the steelmaker?
Yeah, I think again, we are working in this that the sector is using it. We know we have different projects with the steel makers, with part makers, with car makers, and I think that the idea is really reaching this. In fact, ToughSteel has in the partnership the different steel associations in Sweden, Italy, and Spain. So the idea is this, and they can really do it in the production, in the comment, because here you see that these tests look quite complicated. We have a notch, a crack to propagate and nucleate and then test it. It takes, Laura say in the next presentation, it takes some days, but we develop a method that you can do it very, very fast and easy. This is some presentation of that. And yes, I think that steel makers can have this during the production to control. And also you from the working in the workshop or in the lab, you can also implement as a quality control as a tensile test and then verify if the values are within the range you expect it to be.
And the last question from John Lamontanara. I think we already discussed this a bit. How to implement the EWF in stamping simulation software?
Yes. Yeah. Thanks for the question again, because of the time we didn't have time, but maybe in the next seminars we can have a special issue on that. Maybe we can have a special session because in modeling, this is what I learned from Mats Oldenburg here at Solid Mechanics LTU. I remember that he always say that something that cannot be modeled cannot be manufactured, and this is right. We have to model things. We have to estimate from the FEM, and we are in that process. So we are introducing damage models that are having nice results for implementing. So yes, I think from the design stage we can help in that.
Yeah. So thank you very much once more. I suggest now that we take a 5-minute break and see each other at 14:35.
Right. See you all then.
See you. So the clock is 14:35 and we should resume our open day. I hope you managed to see the agenda. I made a very quick update of the schedule to adjust to new times. And what I did was to shorten the open discussion in the end because we have had some nice discussion after the presentation by Danielle. So I leave the word to Pierre Bollen at UCL, and he will talk about the fracture toughness database.
Hello. Hope you can see the screen. So my name is Pierre Bollen, so I work at the UC Louvain in Belgium. And I work with Professor Thomas Pardoun and Professor Pascal Jacques that you have probably heard already. So I will present you the database that we develop in the project. So like David and Daniel say, so there is a lot of interesting data that we need to select the best material or to drive research toward the best steel for the futures. So the database will be hosted at that address on this link. That you can see on the top of the screen. And so there is the layout of the presentation. So it will be all the workflow of the database. So I will present you how to create an entry, the different steps, so you can have a better view of all the information that will be stored inside the database. And I will show you what we have done now to access the database. So we have two different way to access it. So you can search and get ID cards, so that will present all the information that we have for one steel, and you will also be able to create some map of interest, so like some of Daniel showed on the previous presentation. So the database will be public access, but we will ask to create an account. So we can get to you if we see something which is strange in an entry or things like that, and we can keep track of everything. So I will start now to talk about how to create an entry and what are the type of information that we need to enter, to encode. So first we will ask you to encode what are the origin and how you think that the validity of the data, if all the norms are well respected, if everything is nice. This is this step. So next step will be to specify the chemical composition, the steel name, also if there is a standard name for the steel, so we can make search easier for after that, and also if you know the steel producer. And of course, we'll ask you to enter the chemical composition of the sample. We can specify what's the microstructure. So as we see already, microstructures play a big role in the fracture toughness properties. So we'll ask you to specify what are the phases in the steel, and if known, you can also put the volume fraction of its phases. We can give some more information about if there is particle inclusion and things like that, and other indication. You can also upload a micrograph of the microstructure, so we can store the image also, and specify the class of the steel. Next, we have all the elastoplastic properties of this steel. Like you say, it's really needed for the formability and things like that. So this is all the interesting part that we ask you to fill up. Also, you can give all the extra information, so the specimen geometry, the direction of testing, things like that. And we can also upload stress strain curve with different extension. And to the core of that database, we have the essential work of fractures data that you can encode. So we have this part here that is really what is interesting with the essential work of fracture index, with the total work and the essential work also. And you can give more information, and you have the possibility to add a lot more information about everything. Also, which is important, is all the pre-cracking method that you use. You can also specify it. And finally, we have some fracture mechanics data, so which is the G critical index that you can specify, and there is a lot of information that you can put. So like I said, with all the information that is entered in the database, we will create an ID card for each entry. So here you have a look of what it looks like. So we will specify the composition, the steel name, the producer, and everything will be summarized in one ID card for each entry. So one entry will be one steel test in a paper or in a project. So now who can now access the database? So to search into the database, we'll use filters. So here you can see the kind of filters that we have implemented so far. So yes, I will not go into the detail, but you can really pin down what you want, and the result will just appear, and we show you what steel you are interested in. And so this is the page that you see. You will have on top the link to the ID card that I showed you previously, so for each result. And also you will be able to create a graph or maps of properties, so you will be able to specify which will be on each axis. So for example, here we will use the ultimate tensile stress and the essential work for the fractures. And so this will be the kind of map that you will be able to create when you have all data. So here there is 2 dots for each steel, because we have 2 types of pre-cracking method, and you see that on top it's always blunt fractures, blunt crack, sorry, and that will artificially increase the work of the resistance or the toughness of the steel. So this will be all. I will also add in the presentation all the reference of the paper that we will use for the first batch of encoding. So if you want a nice short selection of the best paper about fractures toughness, and more specifically essential work of fracture, you will be able to look into this list. So I don't know if there is any questions.
Yeah, thank you very much, Pierre. It's very nice of the database. We have time for questions. Write them in the chat or just raise a hand. I see nothing in the chat, and I see no raised hands. I suggest that we move on.
I leave the internet to Laura then.
Yeah. So the next speaker is Laura Griffet from Eurocut, and she will tell us about the user guideline. So please, Laura.
Yes, thank you very much, Eric, for your introduction. I will share the presentation.
I guess it are different. I guess it's better if
Sorry.
I will get a job, or yes, I get a job in a company.
Let's see if you can see it properly here.
I was searching.
We do.
Can you?
Yeah.
Sorry?
Yes.
It looks very nice.
Okay.
My
Perfect. So thank you very much. I'm Laura I'm a researcher in the unit of metallic and ceramic metallics in EURECAT, and I will present to you the user guideline for created in this ToughSteel project. And first of all, you can see the index for this presentation. It will have this introduction, fracture toughness, metal sheet methodologies. Then we will see the fracture toughness measurements for material selection, some industrial cases, and some final information interesting. So, first, the aiming for this user guideline is we have seen that using high strength metal sheets, we find. Sorry. We will start with the introduction for this user guideline. As I was saying, we have seen that with using high-strength metal sheets, we can find some cracking-related fractures that may lead to wanting to investigate crackinization and propagation resistance of these materials, which leads to then fracture toughness measurements. And one of the main aims for this ToughSteel project is to make these methodologies to measure fracture toughness accessible for all industries and academic. So we are creating a user guideline to have all the methods and applications all together in one place, so it can be easier to access and then to measure these parameters. As you can see in this scheme for the user guidelines, what it shows first is the different methods to measure fracture toughness values. Mainly, we will focus on the essential work of fracture method that has shown to be suitable for thin ductile sheets. And then we will see some applications of measuring the fracture toughness, how we can implement these measurements to our industrial problems, for example, and how we can help improve microstructure design, select the most suitable materials for the final use, as well as some quality, use it as a quality control parameter. What we will start first here. We will see briefly some of the fracture toughness methods to measure for metal sheets. Already, Dr. Daniel Casellas has presented most of them. We will briefly show how they can be applied in the experimental way. We have seen here the first methodologies that we can find standardized for fracture toughness are mainly the J integral and the CTOA parameters. The first one has some special specimen size requirements, and it makes it difficult to apply for thin sheets. And then both of them show to be complex experimentally. They need crack growth monitoring, and post-processing data is also difficult to do. So we have another method here, which is the Cantier test method. This one consists of pulling this sharp notch specimen up to fracture. And we can obtain here the unit initiation energy and the unit propagation energy. It has been shown that the unit initiation energy can be suitable to describe or estimate crack initiation resistance, but as already Daniel has explained, the UPA may be useful to classify some materials for its cracking resistance, but usually it overestimates this crack propagation resistance due to its loading process, where some compression forces may appear at the end of the testing. You can see here at the left some specimens before and after testing, and you can see it's not possible to break them for these conditions. So another methodology explained here in the user guideline, and it's the most popular one maybe now, or the one that is showing to be most interesting to characterize fracture toughness of thin ductile metal sheets. And also, this one is the essential work of fracture methodology. One of the main advantages of this method it's its relative simplicity in experimentally. First of all, it doesn't need any crack monitoring, or the data processing is not complex. But we need to take some things into account when we want to really test the materials with this method and obtain accurate results. One of the first things we can see, and that we have already commented in previous questions, it's for the thickness of the material sheets. Usually, when using thicknesses of less than 3 millimeters, we will use dent specimens in a tension mode. But when we want to perform a test with more than 3 millimeters, we will use SEM specimens, single edge notch bending. As its names can tell, it's for bending process. And here we can have these two kind of geometries. Usually we will use the dent specimens, and one of the things we need to take into account in this methodology, that maybe it's the most complicated, is when preparing the specimens. They need to be with symmetric notches, and they need to be sharp. But that's one of the points that we will see here, that the notch radius for these specimens need to be very sharp. And we can see here some effects, how the radius depends on the fracture toughness, and at a certain radius this can be well established. But if the notch is the radius is too large, we will have some dispersion on the results. And how we get the sharp notches? First, usually we use fatigue pre-crack notches that need to be performed in specific machines for fatigue pre-cracking and fatigue experiments. So it can take quite some time to perform, and difficult techniques to process. So in EURECAD we have developed a new tool to solve this problem and make it faster and more simple and easier to apply to the industry. And it's a new tool that can create two symmetric notches to dent specimens by a shearing process. You can see here that with the specimen created, we can get these sharp notches that are similar to a fatigue pre-cracked ones. And what's most important about this, first, is what I was saying. It's a fast method. We can see that for fatigue per cracks, we need at least 90 minutes for specimen, while here in 1 minute it's already done. And another important thing is that we have seen that it works for a variety of steels, from CP1000 to DPs, third generation, or pH press hardened steels. So that's a good point to keep into account. This method is faster and allows you to apply the essential work of fracture methodology in a most faster way and without any specialized equipment. With this methodology, we can measure this fracture toughness and use it for what we may need, for example, for material selection. And a new parameter has been defined here, which is the cracking resistance index. It's related to essential work of fracture, but simplifies the method, and it's a way that we can classify materials by its fracture toughness to see which can be more accurate for the intentions we need. This index is calculated by using only one ligament length for the essential work of fracture, and it simplifies that we don't have to use a range of ligament length. That's what we need for the method. In this case, only with one single ligament, the ultimate tensile strength, total elongation, and the specimen thickness and length, this parameter can be measured and can be used as a fast way to characterize or to compare different materials. Next, we can see some industrial case studies that has been performed for real problems in the industry. And this shows some applications for the essential work of fracture methodology. First, we can find a coil-related problem where the initial problem was that the different coils would some were okay and some were not okay, that would show initial cracks when producing these coils. So when testing them with the essential work of fracture methodology, we found that the okay one had some good linear correlation, but in the no okay one, we found some drops in the load. We can see here in the graphs, and then lead to scattering in the final results for essential work of fracture. This was related then to some brittle-like behavior in the surface of the fracture, and then it can show that essential work of fracture measurements are very sensitive to local microstructural defects, which cannot be obtained with different other methodologies. Then the last case study showed here, you can find more in the user guideline, is from an aluminum 5000 aluminum alloy that from two different batches they found from one batch they found that they had some cracking problems when forming, but they made a purer alloy for this aluminum, and this problem they found to be solved, but they wanted to know why. So they performed some traditional tensile tests, and they found that the conditions for these two materials were similar, but they couldn't understand why there were some difference in this cracking process. So when performing the essential work of fracture, we found that the material that was more pure and had less defects was double the essential work of fracture than the one that was not okay. So this way was a good point to show which material was best to choose for this cold forming procedures. So here are these two examples for the use of the essential work of fracture, how we can apply that. And finally, we can see some more information related to this project. You will find soon this user guideline at the website of the ToughSteel project, but also you can already take a look at the CEN workshop agreement that has been developed in the frame of the Form Planet project, where the methodology for the essential work of fracture is being standardized for thin metal sheets. So thank you very much for your attention, and that's all.
Thank you very much, Laura, for this presentation about the user guideline. As usual, write questions in the chat or raise a hand. I see. Yeah, now I saw a question in the chat from Jamie Alonso. Why this interesting work is only focused on thin sheet metal parts and not our forgings or castings from an industrial point of view? Why is it focused on thin sheets and not castings as well?
Okay. Let's see. I think for now we are working on thin sheets. It's these new materials that are being used for automotive. Yeah. Daniel, I think he wants to talk.
Yeah, maybe I can help to answer this question. Yeah, we started with metal sheet because the sector asked for that. It was with problems when it's cracking. We also have some works in casting, aluminium casting. We have two papers evaluating the crash worthiness of aluminium castings. So yes, we applied. The thing in castings is that depending on the aluminium, the toughness can be measured by conventional linear elastic fracture mechanics. So easy fracture mechanics is no problem. For the recent developments in aluminium casting that has higher ductility and higher crash, then the essential work of fracture works. So maybe I can put in the chat the paper because I think it's open access, so I can share with you if you want. Yep. Thank you.
Okay.
You had raised your hand as well. Was that this? More questions to Laura? If not, I suggest that we move on to a presentation of the upcoming events in this project, and Michael Tedesco from CRF will present this. So the internet is yours.
Thank you very much. Okay, now you should see in presentation mode.
Yes, that looks very nice.
Okay, so good afternoon to everyone. I'm Michele Tedesco, and I am the metals manager in the research center of Fiat, a Stellantis company, so a car maker. Before to see the calendar of the next events, I would like to tell you why we are taking part in this consortium and why we believe that these kind of methodologies could help us in the stampers stampers field, metal stampers field. As showed before by Daniel, the evolution of the material, the steel sheet material, changed a lot through the years. Now we are using more advanced high-strength steel or ultra high-strength steel to reduce the weight of our car and so to reduce the CO2 emissions. Unfortunately, the conventional method that we have in our pocket to characterize the material cannot satisfy all the requests that we need in terms of material information to good predict the behavior of the material under the die. In fact, as we have seen in the different case studies showed during the previous presentations, sometimes the simulation and the physical test didn't return the same results. So for this reason, we have to we necessity to have more information, and this methodology, the essential work of fracture, is going in this direction. If we are able to predict during the simulation the behavior, the correct behavior of the material under the die, we can save time because we can decrease the setup of the die, and also costs because we could avoid or the rework of the die or the scrap during the process. So for this reason, we believe in these methodologies, and we would like to spread this opportunity also with our partners and also steel makers. About that, we have planned several meetings, several opportunities to spread this knowledge. We define the different meetings in different topics. So we divided them in training webinars based on the fundamental basis of the essential work of fracture, the academic workshop, so mainly relating to the universities and the research centers, to present face-to-face this kind of methodology, and a wider meeting with the industrial partners, so an industrial workshop to discuss more in detail about these methodologies. As you can see, is planned to make this workshop in different countries. So I believe that you could have the opportunity to take a part of at least one of them. In parallel, we will do also digital courses to spread the basis of the essential work of fracture, and an important topic is the open call, because we would like to collect some experience from other industries that are outside of this consortium, solving their problem in terms of edge cracking. So we will launch these 2 open call, collecting your input. In that, we would like to test for you, and free of charge, the materials that cause you problem during the production. So we will ask you about a brief description of the problem. We will ask you to send us the okay and the not okay material, and in parallel to the conventional characterization, tensile test, micrographic, and so on, we will perform also the EWF characterization to understand if the problem that you have in production could be predicted at the beginning stage using this kind of methodology. I repeat, this is an opportunity for you to understand if there is a way to predict the problem that you have in production, and is completely free of charge. At the end of this experimentation, the main results will be shown as a case study. So we will disseminate this activity. As you can see, the calendar of the events is very full. The next one is in February, the 25, a couple-hour meeting in which we will see the advantages and the limitation of the current methodologies to measure the fracture toughness when it's applied on thin metal sheets. The mechanical principle and the physical aspects of the EWF method, the technical aspects of the essential work of fracture method, and as today we will have an opportunity to discuss together in the open time discussion. To be updated on all our events, I suggest you to visit our website, the ToughSteel website, and also apply on the LinkedIn. So follow the project also in LinkedIn, where we will publish time by time the different events. So thank you, and I suggest to leave the floor to the open discussion to go deeper in the different presentation that we have seen before.
So, thank you very much, Mikkel, for this nice overview of the upcoming events. Any comments or questions about what's going on in the future first, before we start the more open part of the discussion? Now, I don't see anything in the chat, and I don't see any raised hands. So then I will share my screen once more, if I remember how to do that. So then we go to the last point here, our open discussion. And I just wrote down a few questions here, but first of all, I think we should, if there are more questions regarding the presentations we have heard today. I will see if I can manage to see the chat in the same time as I am. So, share my screen.
Maybe I can ask, or just you put some comments to Michele. I mean, we worked together for a long time, and it's clear that the steel sector is growing, is evolving. The materials development for vehicles is constantly changing, and now with electrical vehicles, we see new perspective. So all the works we mostly done was application of fracture toughness on the standage cracking and crashworthiness, applied to bottom wide, applied to fatigue. I'm sure that this will be more development for battery protection, powertrain. So I would like to Michele give the vision from the car sector about the coming mobility and the need for new materials. I know you are an expert on this, Michele, and also we would like to talk about that.
Yeah. I try to connect this request to the Jean Lamontanara question. If the essential work of fracture will be a part of the material steelmaker homologation? The answer today is not yes, but is not no. We will see. We have to collect, first of all, the information about different kind of steel to understand the starting point of each grade. And after that, for the future, I think that this could be something that could be integrated during the validation of the new material, especially if we are planning to use advanced high-strength steel. Maybe will be not a requirement for the low carbon or the microalloyed steel, but for the complex phase, the martensitic and so on, could be a requirement. This requirement could give us the opportunity during the validation to select the best suppliers for this kind of material, and also connected to the what said before by Daniel, to be in safe condition when we make a component that have to, for example, absorb energy or limit the intrusion during the crash. Not only for the battery pack, but also for the main structure of the body in white, where we are using this kind of material. Now the trend is to increase time by time these kind of steels, because we need them for the lightweight. If the lightweight is still important for several aspects. The first one is the CO2 emission, if we are looking for the internal combustion engine vehicles. But also if we are talking about the battery electric vehicle, these kind of steel are necessary to increase the autonomy of these, the range autonomy of these vehicles. And in parallel, there is also another aspects for both of them, the environmental aspects, because if we are able to use less steel, so less steel or aluminum for the new vehicles, for sure our carbon footprint will be lower. So we will also be more clean as company. And this is something that not only the European Commission, but also the other countries are looking for. So the mission of lightweight will still continue.
Yeah, it's nice to hear from the other side of the value chain that is still works to do in materials development and characterization for the vehicles. That's really interesting.
Any more comments or questions? Yes, Per.
Hello. Thank you for a very nice presentation, sir. I have also a question to Michele. I'm a researcher working with numerical simulation and so on, and also work with Daniel for many years in this area. How do you see development of models for the future if you're going to meet these demands with the CO2 emissions and so on? Do you need something? Maybe you can give us researchers something to look at, something we should focus on in the future.
Yeah, the situation, the simulation also give us the opportunity to reduce the CO2, because if we are able to simulate the vehicle crash or vehicle fatigue and so on, we could avoid to make physical tests that are expensive, and at the end we have a waste, because this car have to be destroyed at the end of the test. So the simulation is fundamental on this way. In the other way, we need more accurate simulation to predict in better way and to be near to the reality, to the physical trial, the output of the simulation, because we have seen, especially with exotic material, that the simulation today is not able to predict in a very good way the behavior of the material. So for this reason, maybe the advanced characterization could help you and us to better simulate the material behavior under the die, and not only, also during the crash. So the advanced models are necessary to do that.
Thank you, Michele. I totally agree.
More comments, questions, or discussions?
Eric, I think we have in the chat comments.
I think it was already addressed.
Okay.
During previous question. You referred very nice to this, Michele.
Yeah, just maybe just to end up this seminar, Eric, I think that what the ToughSteel project brings is a nice connection between the basics, as Patrick said, the modeling, also as I discussed about the fracture mechanics and the final part, production. So I think it's a success in the way that the research entities or academia can interact with industries to progress towards a more resilient industry in Europe. We need industries that can efficiently produce components in a sustainable way and an affordable way. So also, Michele said the word is exotic materials. We know what you are referring to. We need something consistent that doesn't change so much from the first to the 1000 part. And I think the materials that you can trust, I think that steel is one of those materials that we can really trust when we build the vehicle. So, as also Michele, as you said, there are many events in the coming weeks that we hopefully the pandemic allows us to meet, because these events are much more efficient if we meet and we discuss together. The networking is crucial for this, so we really hope that the situation is getting better and better, and we can meet all very soon.
So, last chance now. Now we got a question from Donato Pincioli. To everyone that wants to reply, do you believe that the essential work of fracture could give test data for investigating also the materials for the purpose of hydrogen transportation? And that's something we're thinking a lot about here up in Luleå with the big investments in steels up here. It's a difficult question.
Yeah, I can initially ask from a fracture mechanics point of view. Of course, the hydrogen is the devil for materials for steel, so many tiny concentrations can really ruin the microstructure and the properties. The first trials we did also with CRF in another project about hydrogen embrittlement is that tests that are testing very localized material, like the test we show, can give relevant information about local damage. And then this is where is a potential use also for hydrogen. So what we are doing is we are charging specimens with different hydrogen content and then checking how this hydrogen content decreases the fracture toughness. Because at the end, if you have a defect on a structure, this defect will be close to the hydrogen, and the hydrogen will be close to the disaster. So we're trying this. So I hope before the end of ToughSteel, maybe we can have some results back to the audience. Michele, I don't know if you're the vehicles that will transport hydrogen, how you will manage that.
This is very interesting field. Yeah, for that is something completely new. As much as data we have, we could use to predict the behavior. For sure, the essential work factor could be something that can help us to understand locally what is the behavior of the material. And so if the essential work factor is high, maybe the material could be in safe condition also in terms of hydrogen. And in parallel, we will work also in the other kind of methods that are not only mechanical one that you mentioned before, Daniel, to study the effect of hydrogen in the different materials. So this is a green floor to make our research.
Yeah. Exactly. The more data we have, the more we will know, and then the better cars we will build, and more safe we will feel when we drive these cars. This is really amazing. Also for us, again, researchers need challenges. Also modeling part, you also have to model this couple effect of hydrogen and mechanical loads. Not easy task, I know.
Yeah, in fact,
that's a challenge.
Yeah, on that during the other project, the Fourth Planet, we start to describe a method to predict the material failure due to hydrogen embrittlement. So this is something at the early stage, so it's necessary to work on, and for sure with the Luleå University and also the university in Pisa, we will go forward on these aspects.
Yes, this is in the frame of the Crystal RFCS project that we have, just in collaboration with Pisa University, Letomec, and also CRF to progress in this. So definitely interesting.
Yep.
So time is running out and the clock is 3:30. So what remains is to say thank you to you all speakers and all attendees for participating in this open day. And don't forget to sign up for the next event on the 25th February.
Next time together, potentially, hopefully.
Yeah.
Thank you.
Thank you
very much.
Goodbye.
Goodbye.
Thank you. Bye-bye.
Bye.